I'm Ryan Woolley from the Program Committee. Welcome to the data center track. I'm going to get started here with Gabe Cole is leading the track for us, and we'll begin. You want to introduce Gabe? Or sorry, Peter? Great. So I'll hand it off to Gabe to introduce our first presenter.
Thank you, Ryan, and good afternoon, everyone. I know this is an afternoon track, and it's a beautiful day outside, but we appreciate everybody coming in. I think we're going to have some really interesting things to talk about. So first, we're going to go a little bit in a different technology area. We have Peter Gross here, who's going to talk about fuel cell technology and how that can help us move away from the grid and have less dependence on the grid. We're then going to switch over to Jim Smith, and we're going to have and a panel, including Marty Hannigan and Chris Yetman and Peter, to talk about reducing reliability or when is inappropriate in the data center. We then have Lucy Yong from Huawei to talk about data center networking and new technology approaches there. And then I'll wrap up with a update on OpenIX and some of the interesting topics we're starting to delve into there. So with that, I'd like to hand it over to Peter. Just a few words first about Peter. I've known Peter for a long time. Peter was really the founder and the moving force behind EYP Mission Critical Facilities, which at a couple different points in history was the leading developer of data centers or designer of data centers internationally, was sold to HP, and Peter's now at Bloom Energy, leading the Mission Critical group there and helping really to take a technology that was a very interesting technology, but not necessarily suited well for data centers and really putting the parameters around it that make it work in a data center environment. And so he's going to talk about the technology and then how he's really modified it to work in data centers. So with that, Peter.
Thanks, Gabe. Good afternoon, everybody. Thanks for coming. As Gabe said, my background is data centers, but after I left HP, I decided to do something wildly different, and I ended up doing fuel cells in data centers. I don't know how much you know about fuel cells, but I'm going to start doing a very brief tutorial on the chemistry of the fuel cells. The fuel cell is a device that converts through a chemical process natural gas into electricity, which is really an interesting idea. It's fundamentally different than the traditional way of generating electricity, works through three different transition from chemical energy into thermal, and from thermal to mechanical to electrical. That's a traditional way of generating electricity in this world. We simplified that significantly by going through a simple one chemical energy transfer from natural gas into electricity. So very briefly how it works. It starts with a little system that looks a little bit like a battery. It has an anode and a cathode, and has a solid electrolyte in the middle. And the two ingredients, the main ingredients, are oxygen in the air and hydrogen, which is extracted from methane or natural gas through a process called reformation. It's really a very simple process. As a matter of fact, fuel cells were invented in the mid-1800s. That's almost 200 years ago. But nobody was able to make them work properly. When I say make it work, that translates into being reliable and being efficient and having a significant life expectancy, and most importantly, being cost effective. So everybody has tried to play with fuel cells because they're so attractive. But now, for the first time in history, we have the ability to really convert oxygen and hydrogen in electricity through a very clean, emission-free process. So here, essentially, the reform fuel, which contains carbon oxide and hydrogen, is combined with oxygen, and the byproduct is free electrons, some heat, and water, and a little bit of CO2. There are a number of technologies in the fuel cell business. You might be familiar with probably with the PAM technology that is used in automobiles. That's the cold, low temperature fuel cell. But for stationary application, stationary meaning they are much larger in size, so obviously they can be used in data centers. There are only three basic technologies, of which solid oxide is probably the leading candidate for being widely utilized around the world. The basic unit is summarized in these slides that shows the basic element, which is a single cell that produces about 25 watts or so. It's about 4-inch square with a green anode on one side, black cathode on the other side. You put a bunch of those in series, separated by a metal plate, conductive plate, and a stack, which is a cube of about 4-inch side. It's good for about 1 kilowatt, right? So 2 cubes like this would be good for a typical apartment that doesn't have a lot of computers, have only one maybe. So you combine a bunch of those in series and in parallel, and you have a module which is about 50 kilowatts, and then from there, through a combination of series and parallel module like this, we go to megawatts. So this is how a solid oxide fuel cell looks. It has one input, which is fuel, natural gas, and one or maybe two outputs, and that's it. There is a water connection that is needed only for the startup, and and after that there is sufficient water generated in the process, so there is no more need for water. So it's a very simple, very basic device. Moving on to our topic today, how a device like this could revolutionize the data center architecture. As you very well know, I'm sure you do know, the electrical portion of the data center has not changed too much in the last, I don't know, 200 years or so. It's pretty much the same. It's very conventional, very static architecture, not a lot of innovation there. Data center operator have never been very big risk takers. Innovation is not all that big into the data centers. What I'd like to say is that everybody welcomes innovation in data center as long as it's been around for 20 years. If you look at what the data center needs, first of all, you need someone that can put together a slide. Sorry about that. I don't know. I think it's a computer. When I did, it looked really pretty. So there are three things that people care about when it comes to data centers, and the priority might change from one enterprise to another, but essentially everybody cares about reliability, and they care about the total cost of ownership, and they care about, maybe some people care about sustainability and carbon. A lot of people care about security and maintainability and flexibility, scalability. Those things are also important, but these three are probably, and in a conventional architecture, these requirements are unfortunately divergent. The more reliable the data center is going to cost more. It's going to cost more to operate. It's going to be less efficient. Typically, very high efficiency, low carbon installations are not very reliable. and obviously increasing redundancy translates in higher cost. The opposite is true with fuel cells, primarily because you can achieve all these three objectives pretty much concurrently without having to pay a price by increasing reliability or reducing the carbon content. So let's look at the very basic architecture of the device itself. So obviously the core of the device is the fuel cell. The output of the basic fuel cell is DC. In this particular case, the standard output is plus minus 380 volts DC with a ungrounded center point. And from there, for certain application, obviously DC is desirable. Most application, they're not. This DC output is not very well regulated, so a DC to DC conversion is necessary to bring it within some decent regulation parameters, plus minus 1% or so. From that point on, since most applications require AC, we have connected to that DC bus two sets of inverters. I don't know how much you know or you care to know about inverter technologies, but in essence, there is one set of inverters that is connected to the grid, and I'll explain why that's desirable and necessary. And these inverters are what is called a current mode inverter. They don't generate their own sine wave. They need an external voltage reference, which is the grid. Obviously, a little device like this will not move around the grid voltage, so all they do, they inject current into the grid. The second set of inverters used for mission-critical application is a voltage mode inverter, which is very similar to your traditional UPS, solid-state UPS inverter. In the same architecture, PWM, IGBTs, and pretty much the same specification, plus minus 1%, transient response, good regulation. So that's that set of inverters, which is called UPM, uninterruptible power module. I mean, that's the name we gave those inverters, is connected directly to the load, to the servers, to the critical load. In addition to that, there is a set of ultracapacitors. These are storage devices that have the ability to supplement the amount of energy required during a small, fast, transient condition, an overload condition. Fuel cells in general are sluggish, slow. It's a chemical process. So a load step, starting a chiller, for instance, that requires a significant amount of additional current. Since fuel cells go through this conversion process, chemical conversion process, they are essentially relatively small to respond. So in the event with the utility connected there, and that's one of the main reasons it's good to have a set of inverters connected to the grid. But if the grid is not there, having the ability to supplement the amount of energy delivered by the device from ultracapacitors, or that could be batteries, or could be flywheels, or other type of energy storage devices, through a DC to DC converter. That's how we address those type of issues. So this is a very simplified configuration of a mission-critical fuel cell type topology. As you can see here, the two main components are utilities and the fuel cells, with the two types of inverters. The one on top is connected to the grid. The one on the bottom is directly connected to the server. They could either feed the A cord of the server, or they could feed a single core device. So under normal condition, Both sides of the inverters, both sides of the fuel cells deliver power to the grid and to the load respectively. If the utility goes away, the device will continue to run into island mode for a significant amount of time, for weeks or so. And then when the power returns, the device reconverts to the original mode of operation. If the natural gas supply is interrupted, then the load is supplied by the utility. And that's why, especially for high reliability application, having a utility as well as the fuel cell output and the natural gas in operation is desirable. Having two independent sources of power is critical for high reliability application. This is a more detailed depiction of the system. This is a single server. In this case, it's about 250 kilowatts. And as you can see here, it has those black boxes are the generators. Each one is good for about 50 kilowatts. There are 6 of them in parallel. And a device like this delivers 250 kilowatts in a redundant mode. One of those devices can be taken out for maintenance, or it fails, and the system can continue to supply full load to the data center. In addition to that, you can see there the inverters on the top. There are the current mode inverters connected to the grid. On the bottom are the voltage mode inverter connected to the load, and and this is a more clear topology. It's easier to follow this kind of diagram that shows a 1 megawatt system that it's used to power the eBay data center in Utah. There are multiple systems like this, and this type of configuration is used at multiple data centers around the country. And you can see there are 5 250 kilowatt devices operating in a redundant mode. To a certain degree, this configuration mirrors your traditional solid-state UPS with a static bypass, with a dual-core architecture. It's been operating like this for a number of years, very successfully, and the reliability results have been very good. This is another configuration that uses a different set of inverters, larger inverters. This is a multi-bus solution that can go to 10 megawatts or even higher, obviously at medium voltage. On the right side of the schematic, you could see a static bypass that can work in 2 modes. You can use a dual mode type inverters, and in which case the solid state device is operating, the static switch operates in a normally closed mode, and if there is a power interruption, obviously that device has to open very fast, otherwise the entire energy of the devices, of the fuel cells will be delivered back into the grid, which is obviously not very good. And the inverters operate in the dual mode. They convert from current to voltage mode. So this is a solution that it's used for much larger applications, and the typical output here is 15 kilowatt, 15 kV or even higher. As I mentioned at the beginning of this presentation, this type of solution can be used either for AC data centers or for DC. You don't see a lot of DC data centers yet, although finally, after all these years, there is some progress there. A 380 volt data center exists in actually some of them in Asia, in Korea, in Japan is probably leading that. A lot of them in China, although they operate at 240 volts. Some of them in Europe, and a few smaller size facilities like these in the United States. This whole transition to DC, high voltage DC, is still in infancy, although the benefits are well understood, and a lot of people are looking very closely at the next generation data center that operate at DC, where the costs are low, the reliability is higher, the efficiency is better, and so on. So this is a typical topology using the similar kind of fuel cells, except in this case, the vast majority of the output is delivered in the DC output, although there is the option of having an additional DC to AC conversion, providing some of the loads in the data center at AC. This design illustrates a different type of storage. In this case, these are flywheels. As I said before, storage could be ultracapacitors or flywheels or batteries. And this is a similar configuration using both a dual core architecture for both AC and DC. In terms of reliability, we have done a lot of modeling to really understand how the system like this behaves. It's all predicated primarily on the availability and reliability of the utility and of the natural gas grid. And as you probably know, the difference between the two is significant. The gas grid, the gas network is an order of magnitude more reliable than the utility grid, and that's for obvious reason. First of all, because it's all underground, and secondly, more importantly, and you can see that illustrated here, the natural gas grid has a network design, a matrix design, so one failure can be always bypassed through a different path. And more importantly, because the gas supply is so much more reliable, simply because there are so many storage points. Every node has a large tank, so that this country, for instance, can operate operate at full power if the entire supply of natural gas with wells or LNG facility or whatever is shut down, simply because there is so much gas stored in these tanks and the nodes. Coming back to the reliability numbers, as I said, we run a number of modeling using both reliability block diagrams and fault tree analysis. And the numbers are pretty consistent, showing that a system like this, having a average 3 nines and a half availability for utilities using a redundant 1 megawatt system, will have a probability of failure less than 1%, which translates into an MTBF. That's not the best way to analyze that, but MTBF is easier to understand, of over 100 years. And this is a single core reliability model. A dual core reliability model will translate into a much higher reliability that could be the probability of failure to drop to about 0.2 or 0.3%, which is extremely high. So to summarize the benefits of a system like this, and the assurance of reliability, because obviously a new technology like this will always raise questions about its reliability. It's been operating very reliably in the last 3 years, and it's because it's designed for mission-critical application. It has a high level of redundancy built in the system. The system is concurrently maintainable. Every component there can be replaced or can be repaired, monitored without affecting the ability of the system to deliver power. And it has a very comprehensive monitoring system that predicts failures, and it has been proven to be very reliable, and for the large portion of this country, cost effective. So we are very bullish on the fuel cell as the next generation power systems for not only mission critical application, but for delivering power in general. Okay. Oh, any questions?
Hi, Peter.
Hi.
Well, we already know each other, but for the benefit of everyone else, I'm Martin Hannigan from Akamai Technologies. Is there a difference in reliability of gas versus the utility?
Yeah, as I mentioned, the gas grid is 10 times more reliable than the utility grid on average. As you probably know, there are reliability numbers for different utility grids, but because the gas supply is so reliable, there is no record. Nobody really keeps track of the reliability of natural gas. It's interesting, for instance, when the big San Bruno explosion occurred a couple of years ago or so, we had a number of installations within 5 miles of that location, and none of the sites were affected. There is enough. The system has enough bypasses so that gas was able to get to. Sure, if the gas pipe or typically installation like this have redundant gas pipes coming into the facility, if that pipes fails, that's a problem, and that's why for these kind of reliability results, having utility to back up the gas supply is recommended.
So, and then if you don't mind, a question about the reliability model. So if I interpreted the slide correctly, the reliability model was based on gas only and without the utility connected?
No, those numbers are combination gas and utility. And for these particular models, we used a 3.9 availability for utility, which is fairly average for United States. But it has to have both. Without that, the reliability, gas only, the reliability is much lower.
Thank you.
Hi, Neil McRae from BT. I'd just like to understand the economics of this. So, a traditional,
Yeah, me too.
a traditional kind of utility, M+1 has X price and X payback. How does this compare? So, do I spend more money up front, or?
Well, I can only tell you about what my company does. Obviously, I cannot talk about the whole industry, although probably it's fairly similar. It's very difficult to compare this architecture with the traditional conventional topology, simply because with this architecture, you generate revenues as the system ages. If you ignore the capital cost, ignore the operation maintenance cost, the cost of electricity generated by a fuel cell, assuming that the cost of natural gas is pretty average, which is about $5 per million BTU, the cost of electricity generated by a device like this is about 3.5 cents. Obviously, there are other costs associated with that. Now, obviously, when the average cost of electricity in this country is maybe 7.5 cents or so. When you generate the electricity at 3.5 and instead of paying 7.5, you make 4 cents for every kilowatt hour you consume. Over 10 years or so, those numbers add up, and a system like this, even if you consider a fairly significant upfront capital, because this device, this system, is more expensive than the equivalent generator, UPS, battery, transfer switch, switch gear, switchboard, all the associated components that goes to essentially replace the function of a fuel cell. If you, the first cost of this device is higher, but over the life of the system, there could be significant cost savings. If you look at the the entire picture, probably about 1/3 of the cost is the hardware, the first cost. 1/3 is the maintenance over the life of the equipment. 1/3 is the cost of natural gas. For a mission-critical application, you have to consider the fact that in the cost analysis, in the financial model, which primarily the most important components of the financial model are the cost of natural gas, the cost of electricity, the escalation rate for the electricity, the escalation rate of natural gas, incentives. Right now there is a 30% tax credit, and there are some state incentives, and the cost of the displaced equipment. If you add all those things, and you can buy this device or you can lease them so that there is no upfront cash. But on average, any place where the cost of electricity is about 7.5, maybe 8 cents a kilowatt hour, a solution like this makes financial sense. Yeah, you can, we're done? Okay, thank you.
So Marty and Chris, you want to come up and join us? So our next section is going to be led by Jim Smith, who's the CTO of Digital Realty Trust. Jim's been in the industry a long time. Peter was half joking about the industry hasn't changed that much in 20 years. To the extent it has, Jim and a few other people have been a big part of that. When he started at Digital, they were kind of a ragtag collection of leftovers from the 2000 downturn. And today they are one of the largest builders of data center space in the world, and they refined the model quite nicely. And what we asked him to talk about today is what that means, and what that means from a reliability perspective, and whether it's time to start thinking about changing some aspects of that some of our workloads, particularly as we move to the cloud, just don't need the high level of reliability that we've spent the last several years refining. I've also asked Peter and Marty Hannigan from Akamai and Chris Yetman from Vantage to join us for their perspective, both from their current positions as well as kind of historically going through that time as well. I listened to a talk from Peter in London last November when he said that eventually we'll have not just software-defined data centers, but software-defined infrastructure where we'll be able to dial up and down the reliability based on what the requirements and the workloads are. So I think it should be a good discussion. We'll leave some time afterwards for questions. I can talk fast if I have to on the last section, so if we run a little long, we'll make it up there. But with that, I'll hand it over to Jim Smith.
Thanks, Gabe, and thanks everybody for coming. These guys are going to switch out the laptop for a new presentation. But I appreciate everybody coming, and thanks for the words, Gabe. As I talk today, it is great to be here with Peter because a lot of these concepts around reliability, he and his firm pioneered. So I'm a little bit nervous. I kept it at high level so he can't critique my work too much. And I know he will, but besides that, I would like to say it's a really good-looking panel. I love the haircuts on these guys. I feel like the brain power is full speed. And to give a little background on me and Digital, so I'm an undergrad chemist and dropped out of a PhD program right about the time of the Netscape IPO to go start an ISP, and grew up in the colo business and sat out the dot-com bus getting an MBA at London Business School. So part of my job and what I like to do is I like the quantitative aspects. But for example, some of the stuff I'm going to talk about today, and Peter and I were arguing about this last week in a forum, I'm sort of turning my back on the old ways on the math. The sort of data set that we have in our world is so big. I think the failure mode and effects analysis and some of the fault tree work is good and important, but I think, I'll talk about it too, some engineering intuition is just as important, because the reality is we are people, right? Our businesses are run by people, and our operators are people too. But most importantly in the business, right, everybody in this room is getting paid by someone, And as a guy who's on the senior management team at Digital, I'm constantly asking my peers, myself, my customers, and I'm advising my customers is really what's the right balance between expenditure and performance for our business. Everybody would love to have a Tesla or whatever. I happen to drive a Honda Civic because I just take it down to BART. Right? 27,000 miles on a 7-year-old car. I just park it in the parking lot at BART. It's really the only place it goes. And so to me, that's a good balance of expenditure and performance. And so one of the things we talked about with Gabe about this is a lot of people in the network community are looking for lower cost. You know, networks are exploding. The businesses are healthy again. Bandwidth is, people are really struggling to keep up with the loads. So there's a lot more nodes and a lot more gear going in, and it's a competitive and price sensitive business. So how do we trim those costs? And a common concept in the industry right now is lower reliability is a better thing because it might be cheaper. And there are certainly some workloads going that way, and I'll talk about some of the differences between them. But just a quick important point about reliability and availability. They're not the same things. Reliability, generally speaking, is a probability of failure in a bounded equation, right? In 1 year, this thing will fail on this probability. Availability is a more complex equation. Primarily, it's around the service or usability of a service over time. I tend to think of availability as a continuous function, right? So yes, you could say my availability over a period, but that's sort of a recursive, a backward statement. We're trying to build high availability for all of the systems. And the key thing about availability is it's not just reliability of a component, but it's also the mean time to repair and the mean time to restore. So for example, we had a significant event in our portfolio a number of years ago. A lightning bolt struck a switch box, like a pad mounted switch box, one of those big green boxes on the street, blew the thing to pieces. It caused all this downstream problem. Well, the mean time to repair on that piece was a long time, right? We had to fix it and repair it and get a new one. If you go in through the chain of all these mission critical components and how they're arranged, you can have things as simple as a breaker trip for whatever reason. You can figure it out and decide to trip it back. We've had arc flash where people drop equipment, they're safe, but they've damaged equipment. We had a Fox in the substation in Ashburn last week, blew up a high voltage insulator, and the insulator kept up and we were able to restore, but the insulator is now damaged. Right? It's a big piece of equipment that's now going to have to be changed out. So mean time to restore and mean time to repair become really, really important, right? We're talking about moving a lot of current around. There's a lot of energy, some of this, and then you've talked about the mechanical equipment, the rotating gear, craning in a chiller and all these other things can take a lot of time. So my point is availability really works hard, has a really big role to play in your decisions about if you go multi-tier and reduce resiliency. But in general, think of those two basic concepts as the foundation of what we all do in the mission critical space. So I have a thing that I say about the data center business. It's filled with mythologies. If you think of where myths come from, you can imagine prehistoric people sitting around a fire, confused about what goes on in the dark. And our business is really built on myths, and over the years we've dispelled a lot of those. So this is one of those counterintuitive things. I'm saying I'm giving up on the old ways, the quantitative things, but I'm dispelling the myths. Some of those myths are positive, and so I wanted to give you a few positive qualitative myths as we go into what I'm going to do here. And by the way, the main thing I'm going to do here is I'm going to show some data. I'm going to show the reliability data from my portfolio for last year as a way to stimulate the conversation among this group, and I'll race through these as I can. But really the first myth is, and it's important, is there's a balance between complexity and reliability. If you look at organic systems at really high scale and high unit counts, very simple, large-scale organic systems work, and they're very reliable. You may get fuzz around the edges, you may get mold in the middle, but it's one of these metaphors about high unit counts is lots of simplicity with a little bit of chaos works really well. When you're talking about a data center and you put a lot of energy into adding a feature that will counteract or compensate for all the other features, you're going to end up with a complex system that your people can't operate. So if you go talk to data center operators, everybody's got a story about their most famous or their most nightmarish outage. Historically, it's been involved in managing the complexity when the system fires in a certain way. For this audience, people deciding or providing business decisions to their management teams from a technical perspective about should we go with a lower tier solution, my view is it really matters on your workload. If your workload can recover quickly, you probably are a candidate for things that are a little less reliable. There's a lot going on in the industry. Really, a lot of it's coming out of the big, giant, hyperscale web tier. Concepts of, treat servers like cattle, not like pets. These VMs with a lot of orchestration layers and a lot of built-in automation and tooling. Those are the kind of things that build overall IT systems that can restart fast. Now, the challenge is you contrast those to most of my customer base in the enterprise space, or many of your customers if you're a pure enterprise. They've got these complex systems. They're not necessarily well architected with respect application 1 to application 1,000. They've got complex storage, complex network, complex naming requirements. They need a lot more care and feeding when they fail. Those are the types of people who are tending towards the traditional model of high availability, because their penalty, the expected probability of their failure, which is the probability of failure times the headache, is a big impact to their business. So we see things bifurcating that way. Typically, the Akamais and the people who have really elegant applications that are relatively thin and can recover fast, or these giant, Facebook and Google and folks with a lot of VMs and a lot of automation built on scale tend to recover more quickly, so they can afford, in business terms, lower cost. Especially when you talk about scale too, they become more cost sensitive. So it's a positive feedback cycle that's developing new tools and technology. Another key myth is how things fail matters a lot. We brought down Zynga Bingo many years ago. We had a couple sensors fail the wrong way, meaning they broke, and rather than fail completely, they broke and they sent really extreme data into the control system, and then we ended up sucking a bunch of water in the data center and blowing up some servers. And that was a case where the systems we designed and we commissioned, we expected them to work in a certain way, but especially the rotating machinery and the complex machinery, it doesn't always fail the right way. It can fail into states that you've never seen before, can fail into states that you've never anticipated, and there's just too many variables to commission. Another mythology takeaway is invest in reliability close to the load, right? This is an old saw. This is a traditional reliability engineering theme, and I brought it up here because we're going to come back to it when I show you the data. So this really, in this room, so out of people who are architecting systems, who would prefer single corded loads for any reason? All right. Who deploys single corded loads? Yeah. Okay, good. And historically, the view was close to the load is dangerous and power supplies are bad, right? Power supplies are this high failure rate. The reality is power supplies are getting a lot better, and most people have managed through that. But more importantly, 2 cords allows that one layer of management opportunity for funny failures and for maintenance. So we find that in our portfolio, I'll show you some red events. They're about half of them are generally around people with single cords. We've seen a single cord mentality primarily from Yahoo, then move out at dual cord with a lot of the big web scale guys. Then we saw the Facebook team go back to single cord, and thank goodness they're back to dual. So there's not that much single cord out there anymore, but it's a case where it causes us some of the most headaches with interacting with the client. Hey, we want to turn something off, or we want to make these changes. It's really impactful then. And then the final thing I'll say about the mythology on the quantitative side is we talk about in probabilistic terms these perfectly shaped normal curves. The reality is all of this activity is log normally shaped, so it's got some fatness to the tails. And my view is, this is sort of a metaphysical thing, is I think that's because people are involved. Just like the markets are log normal, the reality of these situations and the outcomes at scale are log normal because there's a bunch of people in the room touching the equipment. And those fat tails can really drive your decisions. That's why I go back to this. People in this business, your engineering intuition is very valuable. You shouldn't suppress it. You should manage it and embrace it, especially when you've got these deep pools of experience like I do on my team. Okay, let's get into some of the data. Here's Digital's reliability data for our turnkey data centers. Now remember, our company grew by acquisition. We've acquired a lot of different stuff. We build a couple different models of data center. We have a pretty standard fleet. But when we report our availability, we report about the main core of the fleet because it makes the most engineering and statistical sense. It doesn't make sense to report across the whole fleet for stuff that we didn't build that might be 15 years old. So of course that skews the numbers up. But we have similar availability on the other parts of the fleet, but we really use this chunk as a way to manage what we're doing and make sure we're getting where we need to be. So of course it's a classic 5 nines. We're meeting that, and we're achieving that. But really this is the most interesting piece. And for me as a guy who built the sites for many years, and now I switched to management jobs, and now I'm running operations. You see that total number of availability minutes going up, and then the outage minutes either bounce around the bottom, or at least as long as it diverges, it's critical. So we have a lot more operating opportunity, but we're keeping the outage time down. And this is a little bit of a scrubbed version. I actually have this graph built, and what you really see is a similarly shaped but different positioned graph around human error, right? At our scale, the degree of homogeneity we see in the network and how we operate, this really comes down to human factors. I kind of don't care what the devices are anymore, really don't care about the topologies. All the stuff works. Very few things just blow up. We're now talking about when operators are doing switching operations, can they see each other? What are the ambient noise loads? How do we do training? Do we have enough people on staff? So we're into that human factors. We're starting to look towards aircraft management and cockpit management metaphors to reduce this last little bit. Because you can imagine on either a normal or a log normal distribution, those last gains are really, really hard to get from a margin perspective. But I think what I'm trying to show here is the next bit of detail I'm going to go into is a really valid set of data. So for people in this room, and as Gabe and I talked about what we're going to cover, you know, what degree of reliability do you need? I'm not going to answer the question. I'm probably going to open more than you need. So here's my famous redaction of some information. So this, I happen to be doing some work. This is work I did myself, pulling out of the database. These are all of our events for 2014. I left December out because this was at the beginning of December and I needed the data to do some work. And one of the things I found was we had a particular cluster of generator events that had a certain set of characteristics, and I highlight them because I'm going to take them out of the data. But I didn't want to give too much information about what they were and where they are. But I think this is a point about this type of engineering, and going back to intuition. Strictly speaking, any sort of math or FEMA type work would not have predicted any of this. This required the human, right? Humans are good at pattern recognition. This was me sorting through 700 lines of data. You know, what's going on, what's going on? I recognize a pattern. And this generated a pretty meaningful and important piece of maintenance work for us that's ongoing, that's going to end up saving the company a lot of money and making sure that our sites are more reliable. So once again, you need interaction here. You need people to be thinking about what they're doing. So after I strip those out, I also strip out the anomalies we have in our systems related to rotary systems. We have about 50 rotary UPSs that they have some special characteristics, so I pull those out because we're not adding any more of those. But this is the case for our network, right? And this is, you know, almost 1,000 megawatts of data center, 25 million square feet of white space. These are just the events. These aren't outages. These are the things that we notify customers and notify the management team about. So this could be as simple as a UPS went into bypass, a chiller had a fault that required to take it offline for maintenance, right? This is by definition a broad approach so that we're being more conservative in our communications with customers. But just take a look at what you see in there. So fire alarms, they're a huge pain in the ass. And fire alarms are service impacting because when a false alarm goes off in a building, we have to evacuate people from the building. We consider that a service impact, right? If customer wants to be in the building and they have to leave, that's bad. So there's all these funny little things that happen in there. Leaks, right? And that could be a roof leak, that could be a pipe leak, that could be a fuel leak. Leaks are a pain in the butt. Security and BMS and network, right? We run a big network. It's low traffic, but it's complex, and sometimes we lose visibility into a site, and the guys have to go on manual rounds. Well, that's an impact of service. Now, the real most important thing is this one. This is where we have outages. So these are what we would consider a red event. So this is an impact to service. Generally speaking, that would include loss of load, and by category. PDUs, UPS, RTU for us is rooftop units. We use a lot of rooftop air handlers, and that's a newish product. Now it's a couple years old, but we were debugging some of that during this period. So if you see PDU, UPS, and DC plant, those things that are close to the load are the things that have impacted our customers. Now, interesting on the PDU, that's a pretty broad definition. About 3 of those are single circuits, right? So out of all these millions and millions of square feet we have, we're tracking single circuit outages. Some of those might be a customer overload, but that's okay. If the customer overloaded it, it's up to us to train them not to do that. We still count that as a red event. Occasionally, you'll get an output breaker on a PDU, so you might drop a busway on Starline or something like that. But generally speaking, the ones on the left are, especially in the PDU category, are relatively small impact. UPS invariably ends up being some sort of complex activity during maintenance that brings down a whole system. So those are much more impactful. Rooftop units, if they impacted service, that means the whole network went down. We had some funniness with the controllers that turned themselves off. And then DC plant, that's probably a charging current failure. And then utility and switchgear. So now if you toggle back and forth between some of these, you see utility, I'm almost 90 utility events. This is globally. And this is anomaly, guys going to bypass. Typically, probably 70% of these are gonna be the utility has an interruption for momentary. Maybe half of those you go to gen, but these are real small things. They don't really result in many outages. And in fact, if you go look at these two events, they would end up in a case where somebody was managing a UPS on bypass during maintenance, and we happen to have a utility interruption at the same time. And that's one of the key takeaways from these red events. They generally speaking are compound failure modes, right? If you have the UPS on maintenance and there's a failure event, right, the UPS or the utility goes out, well, that's two events, right? It's not just one. Very rarely in our portfolio, and most people's portfolio, does one thing blow up and everything goes haywire. I will point out fire alarm and suppression. That was a gas discharge, accidental by a third-party technician, so that was not a good deal. So the soft conclusions you come from these are, from a service perspective, it's about events, not outages, right? You'd be shocked at how many customers complain to us about loading dock, fire alarm, security access. Those things impact customers just as much as load. The red events bifurcate into two sample sets. As I mentioned, these sort of complex things with big systems, typically maintenance is involved, or one person where there's one breaker or some circuit being added. In all the cases, change management and change control are really if not a root cause, a contributing cause to the interruption of service. Change management in this industry used to be non-existent. Now we're following a lot of IT metaphors and focusing on change management. Our customers have forced us to do that because they start with change, a lot of the financials, for example, start with change management at the application layer and take that all the way down through the physical layers and expect us to match those protocols. We as an industry should really be proud of what we've done. We've really professionalized that and brought our availability numbers up. So now, the reality is, back to Gabe's topic, is, well, what should we do? How do we reduce our costs? If you have automated systems that can restore themselves fast and reload fast, you can probably benefit greatly from lower reliability systems. Now the question becomes, how do you buy those, right? So if you're at 200 kilowatt scale and you want to buy an N system, something sort of 3 nines of availability or reliability, it's very difficult for service providers to do multi-tiering provisioning that's small. Right, anything small, we build a 2 megawatt site, so 1200 kW of UPS, something on that order. When you guys as a community ask me for 200, 400, 50, 80, 100 kW, to make changes at that scale, the cost per unit goes really high. So the reality is our business is getting pushed and there's a lot of pressure, and some of our competitors have done a pretty good job of saying, we're gonna build a bigger system and have multi-tiering in the same room or the same facility. And so that's a nice product differentiation with better price points. Now, the bigger question is, how much savings can you get, right? So if a $10 million data center, the generator's $1 million, the UPS is $1 million, you can start carving out these things. But if you guys went back, looked at my red events, are you really gonna take out the PDU? Probably not. You're gonna have those failures. You really have to tighten up operations. Are you gonna take out the UPS? Maybe. There are some alternatives there. We would love to get rid of batteries. We'd love to get rid of 7 minutes of batteries. There's some chemistry and engineering reasons why we need to have those. The air handlers, that's sort of an artifact. We're not going to get rid of the utility. One thing that's, I think people read about now is Facebook going up to Sweden, the Google team, they talk about really, really high availability utility systems at high voltage, 100 kV and higher. I think that works at HV, but it probably doesn't work for the rest of us, right? If you're building a 50, 80, 100 megawatt site, like a semiconductor plant, you can go find the right utility architecture. For most of us, even at my scale, it's relatively rare. Like I said, we had a substation in Virginia the other day go down from an animal, a fox in there. It happens, right? That's in Dominion Power, a regulated market, some of the best engineering in the world. You still get these effects. You really have to pay attention to really get utility availability. So where would you go, right? What would people leave out? And I think of it as, you can have a powertrain that's thin or thick. My sense for this group is you want to have a thinner powertrain, right? Maybe an N system with all of those components in. And then the trade-off from service providers is you're going to have some planned downtime for maintenance and restoration type activities, right? Everything's going to need to be checked at some point. If you take that line or that length of system and you start trimming elements, that's another way to do it. But either trimming in the front end, you're gonna get less features, I can't plug as much stuff in, or trimming at the back end, you're gonna potentially end up with a longer outage at some period. The final thing I would ask is, what's the cost of multi-tiering? You know, we have this sort of monolithic product. We build it at a really good cost. It's very easy to manage. As we start adding different products, we're adding product managers, we're increasing the financial risk of doing the wrong thing, right? If we build a product that doesn't sell, or we pick the wrong bet, or in Dallas, for example, we build the wrong thing and we can't sell it, that's a huge impact to the business. It may just be easier to take one product and just relentlessly drive the cost down, you know, sort of like the Toyota Camry type approach. So with that, those were my observations. I think the key thing I found when people ask me to speak, they're really interested in seeing actual data. Here's some actual digital data. It's relatively well scrubbed. You know, we share this stuff pretty often. It's no secret sauce here. We're all about open and honest transparency with our customers. I don't think anyone would disagree that their lives aren't like this in other parts of the service provider space as well. So with that, Gabe, did you have some ideas about how you wanted us to go next on the panel?
I'll lead it off with a question. I'm tempted to ask what happened to the fox, but I fear
The fox.
I want to know
I'll tell
what
you,
happened to the fox.
The photo, I can show you in private. The photograph is a little too gruesome. He did not vaporize, but there's blood and there's it's just I was like, this is perfect. I can show, and it was just too gruesome. It's not appropriate for the public. Yeah.
Okay. So, I mean, this is great. This is a lot of data. I mean, it looks like you got a really good process for how you go and look at this. My question, and maybe we can use this to kind of then throw it open to the panel, and then maybe other people will ask questions along the way. I mean, there's a lot of data that goes behind this. There's a methodology that goes behind this. You go to the other side, the user that might have 2 or 3 data centers. Maybe it's myths, maybe it's knee-jerk reaction, maybe it's fear of their boss, maybe it's fear of their shareholders. But you know, there's kind of this mentality in the world of whenever anything goes wrong, you have to fix that everywhere.
Right.
And you know, how do you really think through that issue and decide if that's just a one-time anomaly that's never going to happen again, and I just put it in the back of my mind and never worry about it,
Yep.
versus when you make that knee-jerk reaction?
So this is a critical question, and I've got to be the one to answer because I have the scale, right? And this idea that Gabe talks about is there's a generation of operators, and it happens to people today. This happened to me one time, and it was so bad, I'm never going to let this happen to me again. And you think about how humans evaluate risk. We're terrible risk engines because the risk to us as individuals, our brains are not wired to do a good objective evaluation of risk. So you see lots of features built in from these mythologies of things that have been added. I'm never going to let that happen again, so I'm only going to do seamless welded pipe for my chiller plant for the rest of my life. Well, there's been so many of those stacked up that people have spent literally $1 billion wasting money. So we do it a couple ways. One is we talk about intellectual honesty with the work that we do with the operators. And so we might be, some of our operators, we might be talking at too high a term, you know, too high a level about some of the analysis. So we make sure that the intermediate tier of managers are teaching some of these concepts and teaching reliability and availability. We have a number of textbooks that people are required to read. So one is to depersonalize and dehumanize these things so they're not related to the people that happen. Our industry's not always been good at that. Some people in my company want to fire first. I haven't fired anybody since I took over operations. I don't intend to. I'd rather rehabilitate them all. But I think it's the function of having data like this that we can then compare events to. And look, let's say something really strange happens and causes a big outage. It might happen tomorrow again, or it might not. You have to have a deep understanding of probability to really evaluate these risks. And interacting with clients that way, we have some sets of clients that are fabulous and some that are really, really difficult. If you're a small site operator, this problem amplifies by orders of magnitude because you don't have the luxury of the data that people, you could even take my data and your boss isn't going to buy it from me because he's not the guy I didn't suffer the outage. Any other perspectives? And Peter, your microphone, you need to.
Just want to add one comment here. Probably the most important metric in this business is risk. We talk about risk all the time, and intuitively we kind of understand what that means, but very few people take the pain. Actually, it's very difficult to do that. Very few people take the pain to quantify risk. Risk is, as you probably know, defined as probability of failure multiplied by consequence. So if the probability of failure is high, but the impact is low, the risk is probably not that great. Just coming back to Gabe's comment, if one event takes place, but the likelihood of that event to happen somewhere else is small, although the risk, the consequence, the financial consequence is high, maybe there is no need for the entire industry to retool or reconfigure. But the point I'm trying to make is that it's when you try to really quantify risk, the only way to do that, unless you're the DRT that has this enormous population, the only solution is to do a full PRA, the full model, because there is not enough data. There is not, from a statistical standpoint, the population of systems and the age of the system is not large enough to provide statistically meaningful data. So that's why the model is so important.
Model to inform, not to decide, right?
So when I look at reliability, Jim, I look at it from a perspective that is more cloud focused, and let's not get hung up too much on the definition of cloud. It means a lot of different things to a lot of different people. To me, it means it's a distribution concept that allows me to scale across the internet. And when I look at reliability, and I actually look at N, and I want N delivery because my N is really multiple sites in multiple locations, whether that's a metro, a region, or a country. So for example, if I've got 5 different 400 gig workloads in a metropolitan area, theoretically, those sites at N, with the exception of critical components like storage and whatnot, my reliability model is really 3N, 4N based on the distribution factor, not the load factor in the data center. I completely agree with your conclusions with respect to component failure, UPS, PDU. I would, even in a single corded environment, I don't know that I would advocate for complete removal of all of those components, or even single removal, with the exception, I have to think more about this fuel cell stuff, but PDU, for example, on a single corded environment, which typically happens today for most of us that use single corded approaches, UPSs, the UPSs are redundant. And right off the bat, connecting to the line with a single cord almost dictates that you're already overbuilt when you're N+1 through the rest of the configuration. So what I'm looking for in the kind of data that you present is, how can I pare down? I want single UPS. I want open-close bypassing the UPS. I need an automatic transfer switch in front of it for maintenance so that your people can do the right checks on it. And I need utility configuration. So I need the option to be able to configure based on, do you have 2 utilities? Do I actually need a generator if we run the Markov chains on the reliability? 2 utilities and I come out at 4 nines plus 7 plus 8? Maybe not, but that's a decision I want to be able to make. Or perhaps you have 3 discrete utility grids that are connected to your medium voltage substation with N1 to the facility. I may not need a generator at all. And that's how I look at N.
Yeah.
I have a question.
Go ahead.
I'm Stefan Engström from ENA Nashville, Tennessee. Your statement that the availability is sort of a log normal over time piqued my interest. Is that kind of some sort of Kai-by-eye observation, or is it something underlying that makes you say that?
So I think a lot of that is conjecture from me, but I'm a relatively deep student of probability, both in business school and in financial markets. So if you read about these black swan concepts, and if you look at actual market returns, they're distributed that way. And so the answer is, well, why? How should they be there? My view is that that's the human factor. Right? If you look at the shape of the normal curve, it's got this E in it. That's where it gets the shape. I think the humans and their participation in the market, their participation in human factors that influence my red events, I think is what makes those fat tails. And so I think we could probably go prove it over time if we had some time in our data, but we need to focus on other stuff.
I mean, in market, it's the product of events that is stack up after each other, and that provides a distribution. I don't really see how that plays in.
No, I think it's, well, I think it's a similar thing of these unknowables, like the unknown unknowns, if you will,
Oh.
related to, you know, we write good methods of procedure, and the guys follow them until they don't. And we have good change management that works until it doesn't. And I think that, to me, is that feel. I couldn't prove it mathematically, but it's that, like I said, I'm comfortable calling it conjecture.
That's interesting. Thank you.
Russ White, Erickson. Two questions, actually. The first is, you said you have a few books that you require people on your staff to read. Could you tell us what they are?
Sure, the first one is Nicholas Somerville, Basic Reliability. It's a pamphlet, it's, you know, 150 pages. We can send them out, or Dave can send them out to distribution.
Because I can't write.
Another one is a horrible textbook that, it's fun to read, don't do the exercises.
No, that's fine.
It's called Reliability
I would be
Engineering,
very
I don't know the
curious.
author,
Yeah,
yeah.
I'd be curious to know what.
Because remember, like, one of the key things about the data center business and our mythologies is we're this closed group, you know, NANOG is this closed group. There's metaphors for all this stuff that are way better done in automotive, nuclear, medical. Another good one is Checklist Manifesto by Atul Gawande. He talks about how human factors in the surgical suite drive infection rates up, you know, and there's all these little things. So there's a lot of other research, and one of the challenges we've had is trying to bring other industries in. Like, I always used to, people would tell me about piping. Well, the piping's got to be dual looped and all this thing. I was like, well, BP is one of my customers. Can we call the BP pipe guy? I think he's going to know a lot more about piping than anybody in the data center business. And so I think our industry's resistant to that. So that's one of the challenges, is taking those.
Yeah, I would actually agree with that. So my second question is, in these red events, there's obviously a come down and a bring up, right? And there's obviously some amount of time that it takes to bring all these systems back up. Do you have a lot of numbers around the events? Do you have any numbers around what takes the longest to bring up, first, second, et cetera? I
Right.
mean,
So-
where could you as a data center operator improve bring up
Yep,
to reduce the MTTR
yeah.
rather than just the MTDS?
So I wouldn't be comfortable sharing those, and other people on the management team would probably give me heat about it. But I will say, for example, my rooftop units, those are scenarios where we have a slow, like in one case, a number of rooftop units with a common controller network, a controller went offline, and I still haven't gotten from the manufacturer what that means. I mean, we tested the thing in commissioning, we turned it off, but when it goes offline and doesn't lose power, it has a different failure mode than when you restart it. It turns all the other ones off. And the suite we were in with the customer was pretty lightly loaded, so it had this persistent, long buildup, but the communication of the temperature controls were in the controllers. So we didn't catch it until somebody went by with rounds just before the customer equipment started to fail. So cases like that, you have these broad impacts that have a long cycle, and then it takes a long time to figure it out. So that you're spot on. I don't know as much about customer systems and how they're impacted. You know, some guys focus on storage or whatever, but for us, what we focus on is rapid reaction.
Okay.
So
that's
we
what
had
I
to
was
teach
trying
our
to figure out.
teams, we had to say, brief notification first and then action, right? Don't sit down and tell me, well, we went to the suite and found that the controller was off and no, like, hey, I'm having a problem, call for resource and get in there and troubleshoot. And then we have an incident management system where somebody else does communications, et cetera.
Great. All right, thanks.
Yeah.
Something to help with an answer on that in regards to servers, right? When you're taking a look at what happens within the data center, what you're going to find most of the time, at least in my experience and places I've been, storage needed to come online first, right? And then right after storage came online, you put a lot of your databases online, because if they're not online, your applications aren't going to work. And they do tend to congregate in the same cabinets. And so a real simple thing when you're working with a provider, so like DLR or like Vantage, is to understand how you want that power to come back online.
Right.
And a lot of times we can work with customers and say, you know what, we're going to hold it off until you tell us. Or, for example, they're just going to shut off all their in-rack PDUs. We're going to light up the busways or whatever else is required, right, and then let them put it on themselves. But with a lot of technicians, and at one point in time, I had over a couple hundred literally just fixing machine, servers. What we did was we color-coded the cabinets, because you tend to actually put things together for their common use. And so if you had a bunch of storage cabinets, what you did was you colored those and you just said, I want you to do this color first. Then when they were done with that, you knew the storage was spun up, they immediately go over and light up the database servers. And again, it was cabinet at a time. And then after that, you lastly go to the VMs. And then that way, what happened was, is when all the VMs come up, everything they needed for a resource was already running. The network was already running. By the way, that gets its own color code, right? Everything else like that. And it will cut back on your mean time to recover significantly if you actually just phase it.
Drill it, right? Do it as a desktop study.
And from the user perspective of another data point, and I don't have a hard data point that I can share, but in the last 5 years, in terms of total data center failure out of our entire basically portfolio of data centers, multiple tens of megawatts, one. With respect to the N versus multiple N approach, just like Chris said, there are some components that in the event that they do fail, they need more care and feeding to get them back up. But the days of having to run around the data center and power cycle every single PC or computer that went down in a failure are fast coming to an end. Things tend to come back a little bit better. But that's why the tiered approach is effective, because you can keep your databases and your storage on 2N or multiple 2N, 1 plus 2 or A plus B, and take the less risky or the components that you will single cord. I mean, single cording implies that you're not overly concerned if you have an event with it, that you're willing to accept the risk of a single power supply and a single socket to get downstream.
All right, thanks everybody for your time. Hand it back to Gabe.
So thank you, everyone. That was very interesting. We're now going to make a little shift, and Lucy Young's going to come up from Huawei to talk about new technologies in networking within the data center, and this is kind of an interesting perspective. I think that I was very intrigued to hear it. As a participant in OpenIX, and Marty is too, we spend a lot of time talking about the data centers and the macro network. And as you go to the world of open compute, they spend a lot of time talking about what Chris just touched on, of the servers and the storage and the the networking communication amongst those components. But the entirety of the data center networking, particularly if it's a multi-user data center, is an area where not a lot of people have expertise. And so I think the next talk is going to be very, very interesting. So, Lucy?
Okay, good afternoon. My presentation is about using this BGP inter-AS options for those data center, virtual network, and WAN VPN interworking. First things, why this interworking is needed. So today, a lot of data center operator offers those kind of cloud services. Some example I gave here is suppose the enterprise Orange buy those cloud service from one data center provider. That cloud services, the requirement is that cloud services need to only accessible by those enterprise side, at those enterprise side. And the data center provider using a lot of VMs and the storage to run such cloud services. Another example here is an enterprise such as the Blue buying those computer resources from a data center provider and require running this enterprise application at this data center site, which running also using a lot of VM and also the storage. And the requirement, the same thing is those applications only can access through those enterprise side. So all these kind of cases that require this service privacy and only can access by at the enterprise side. So really, in the virtual network, need to be running within the data center as well as in the WAN network. So now, okay, sorry. Now we look at this new technology developed in the data center for targeted the virtual network. It's really the virtual network technology that fit in the data center well. This technology, VPN technology, is initially also driven by this server virtualization paradigm. And as a result, this technology decouples tenant, the host, tenant host from data center physical network. As a result, the tenant host is no longer constrained by data center physical network subnet, and also allow the tenant network using their own address space. And also, that's one data center physical network can support many tenant networks. And also, the tenant VMs can move from one server to another server without requiring any reconfiguration. So these are the characteristics that's the technology developed in the data center virtual network. And also this technology adopted those concepts. This is a software-defined network, which is using this centralized control plane as the virtual network control plane. And also this decouples those control plane from a data plane as this SDN technology trend. And also the control plane, the bending those VN layer to the VN transporter layer by doing this inner tenant address mapping to the tunnel mapping. So this kind of a little bit different from those traditional VPN, BGP-based VPN technology. Also at the data plane, this decouples those, that in the data plane, it is a couples those the VN layer and the VN transporter layer. And that means it's at the forwarding, it's based on this, the tenant endpoint to this tunnel endpoint, the mapping. And also tenant package is always encapsulated and delivered using this IP tunnel. Because within the data center, assumption is there's no MPS available. So this is also different from traditional BGP MPS-based VPN. So why we want to use what's the motivation to using this inter-AS option for such kind of interworking? First thing is, as we're, the use case we just talked, the tenant network in the data center need to communicate with the tenant side, which is outside the data center, and in the private and the secure manner. And also, the BGP-based VPN technology has widely deployed in the one service provider network. And some tenant sites already use those kind of BGP-based VPN to interconnect their tenant site. And also the data center and the one service provider, they usually belong to the, possibly belong to the different administration and also different ASs. And then next thing is, both this the data center virtual network and also the one VPN are VPN technologies. And they're both using the tunnel technology to deliver those VM packages. So really leveraging existing the BGP VPN inter-AS option, it is desirable for such kind of interworking. So about this inter-AS option, it's described in the RFC 4364. I'm sure a lot of people here are already familiar. In that draft, actually described the several options, named as option A, B, C. So rest of slides, I'm going to talk about those options. how can apply in this space. So first thing is option A. The option A is really required to configure sub-interface, VLAN-based sub-interface between those AS board routers. As you're showing here, the one side is on the one network, another side is on the data center network. So between the AS is configured sub-interface, VLAN-based, and each sub-interface need to map to the one virtual network, as shown here by this WAF table. So effectively, this AS border router is running as a PE equipment, as a PE component, and hand off those the VN to the customer. So both the one side border router and the data center side border router running as a PE, so just peer together through those sub-interface. So this is the option A. So this option A allows this one-sided network and also data center network can implement VPN independently. No any the interworking there. It's just like a traditional customer handoff. So this, although this option A is simple, but they have a lot of the weakness. I'm going to talk about it later. Then talk about this option B. The option B essentially is required between those the border router interface to run those MPS. Then for this option, there's no need to configure the sub-interface over this between the AS border routers, and also do not require those AS border router to maintain those WAF table. So really don't, during the operation, there's no table lookup at the AS border router. So the package across this AS border router is really the MPS the package, label the package. Each label will be represent one to a one logical network. So when using this option in this space, when doing this data center VN to interwork with one VPN, there's issues because within the data center, those tunnel is an IP tunnel. But in the one network, those tunnel is a LSP path. So to make those interworking, it's require those AS border router to stitching between the IP tunnel and the LSP path. So this is different than just between the PE to PE interworking in the traditional option B. So now we look at how we can improve this AS border router at the data center to support such the stitching. Before we look at this operation at this border router at the data center, first we look at there are several ways to implement this option B at the data center side. So here we list the two cases. We call this vanilla option B case. The case one is assuming that the NVE in the data center can support the BGP protocol. And the case two, assuming that the only NVA in the data center can support the BGP protocol. So first thing I'd like to explain about this term NVE means this network virtualization edge. And that is the component being specified in the NVO3, the framework. That is RFC 7365. And another component is the NVA, which is the Network Virtualization Authority. NVA actually is the control plane for the NVO3, and the NVE is the data plane component for the NVO3. So as we're seeing, both case one and case two can support this option B. So for the case one is NVE support this MP BGP protocol. So it can directly exchange the VPN route with the remote, the PE, which on the another AS. Or this case 2 is only NVA support this, the BGP protocol, then using the BGP protocol to exchange the VPN route with the remote PE. However, for both these cases, the board router is performing exactly the same function. That means that the board router do have this, do not need to have this, maintain this VRF table, WRF table, and no need to configure the sub interface. Sorry, I realize this is my old version, I think. Anyway, okay. And also this, the board router performed exactly the same stitching, the function in both cases. So that's where I see. So I was seeing this, yeah, in this and both cases can support it, but behavior at this board router exactly same. So now we look at this operations in the, at this board router. This in the control plane, really this board router need to allocate a VNID per VPN label when getting the route from one side. And also need to allocate this MPS label per NVE and the VNID when getting the route from the data center side. This VNID stands for this network virtualization identifier. That's also a standard term used in the framework. So in the data plane operation, really this, the board router need to maintain this outgoing forwarding table, which have the entry to mapping this VNID to MPS the label, as we're showing this table 3. And also maintain incoming forwarding table that have the entry to mapping MPS label to this NVE IP address and VNID. So during the package transport, this receiving the, when the board router receiving the package, they will just directly perform this the tunnel stitching. That's between the IP VNID and also MPS label. So this operation has no any change on this one side, the board router. It's just the data center side, the board router need to perform such special the tunnel stitching. So this is the operation at board router data center side. There's another option B implementation at the data center side, as we name this as a partial option B. So in this case, between this the AS board router that's performed exactly like option B. However, on this data center side, the AS router need to maintain this WRF table and have this MPS label to map to the WRF table, then have internal interface to map to this the VN virtual network in the data center. So this is another way to operate the this option B. So for this option, this BGP protocol need only run on this AS board router. So within the data center, you can still using your own the VN implementations. So other things is the WRF table has to maintain in the AS board router. So models look like the board router running the board router as well as the PE function. So this is another way to implement option B at the data center side. So now we look at this option C. That's also possible to apply to this space. Essentially, this option C specified in the 4364, it is using the eBGP protocol to establish a tunnel between the PEs that reside on the different ASs. And using that tunnel to run those, the MP-BGP protocol directly. So as a result, the board router will not board router only exchange those PE route, were not aware those the MPS BGP at all. In saying it's another word to say is not aware those the VPN at all. So when using this option in this space, and again in the data center, we could implement either this option. We could implement this case 1 and case 2. For the case 1 is the BGP available on the NVE. For the case 2 is BGP only available on the NVA. So this figure we're showing here is assuming this BGP only available on the NVA. So apply the option C here is the remote PE at one side, or using the BGP, the eBGP, to establish the tunnel between the PE and the NVE first. Then between this NVA and the PE, we're running this MPBGP protocol to exchange the VPN route. Then this still require this the board router at the data center to perform this stitching, because on the one side it's running this LSP tunnel, on the within the data is running the IP tunnel. So that still require those performing this stitching. And this VPN route will be only exchanged between the PE router and the NVAs in this case. So now we look at this operations at this board router at the data center side. In the control plane, from one to data center direction, the board router will be allocated an IP address per each remote PE. From data center to the one side, this board router will going to allocate a label per each NVE in the data center side. So as the result, in the data plane, it can stitch in this IP tunnel and the LSP, IP tunnel and the LSP tunnel. When the package is coming from each direction, then you just perform those, the tunnel stitching, where that means that you don't have to do any the payload lookup, no WAF table lookup at all. So to do this operation, the one constraint is the operation rule is to partition those VNID space into the this lower 1 million address. This is because in the NVO3 currently this VNID address space is 24 bits. However, the MPS label is 20 bits. So having this the VN directly working, just stitching the tunnel, then that's required this allocate this lower 1 million the VNID space for the inter traffic, and for those rest of the address for intra-DC traffic. This to support this solution, it also requires some enhancement in the BGP protocol. That requires some new CIFI to support this network route information that contain the NVO3 tunnel information, such as the tunnel type and the tunnel endpoint address. So this is for option C to use in this space. So there's many different implementations in this space. Really, each one can apply to certain environment. There are some pros and cons for each operations. And really, we see this inter-AS option is necessary for when those data center operator and the one operator belong to the different administration and also different ASs. We also have some comparison to see those solutions. On the first top 5 is this comparison to the implementation at this AS border router. And for the next, those blue marked item is the comparison for solution itself. So for the consider about this, the board router implementation. And as we point out, for sub-interface configuration, that is only required by this option A. And for the WAF table maintenance on the board router, that's option B, and option A and the partial option B required to maintain the WAF table. So that when we say to maintain this table, that means when receiving the package, your decapsulated package, then you have to do this table lookup. And in terms of configuration, the option A is the most complex because required to configure this sub-interface for each VN. And both the operator have to agree on which the VLAN ID to use for represent which VNs. So all then perform some manual configurations. And the vanilla option B and the option C, in terms of configuration, is quite simple. But the option B, the partial option B, is also requires some additional configuration. In terms of the scalability, as the option A is the worst. And option B, vanilla option B and option C are good. Option C actually is the best. Partial option B, it is better than option A. However, it's not as good as the vanilla option B. In terms of hardware support, the option A and the partial option B, existing hardware are already supported. However, for the vanilla option B and option C, some hardware may require some the enhancement to able to perform this stitching, the MPS tunnel stitching, tunnel and IP tunnel stitching. So in terms of the solution, from security perspective, the option A is the best because option A is just like your handoff to the regular customer. So at this the PE, you can set up some the policy, you can do some filtering things. However, the option B is compared to A is weak in terms of security, and option C is the worst case for this in terms of a security perspective. From a protocol perspective, to support option A and the partial option B, existing protocol already supported. However, for the vanilla option B and option C, there's some protocol enhancement required. It's mainly is how the BGP can carry those prefix tunnel information. And in terms of the solution complexity, I think the option A, everything implementation-wise is simple, although it's a configuration maintenance is complex, but the implementation itself is quite simple. And vanilla option B is in the moderate, in the middle, and option C is the most complex in terms of implementation. However, from a maintenance perspective, probably option C is simple, as we just point out here. Okay, so I have a point out, explained about how those inter-AS options can apply into these spaces. There's different implementations, and this implementation also required a different operation at a board router at the data center. And we do want to get some feedback from operator on these options. First things we like to see which option to fit your environment better. And also we hope to hear some operator can share their operation concern and experience on those implementations. And also, it's possible we want to hear if any desire for additional technically to make those those implementation running better or make your the operator life easier. And as we're seeing, all these options are described in this Internet IETF draft. We are trying to standardize those kind of solutions. That's a benefit for operator and also benefit for the vendors. And if any operator in this room interested in this subject and want to work together, please voice up on the mic or can talk to me directly after meeting. So we like to hear some feedback. So that's it. It's my presentation, and I'd like to see any questions.
Rafael, I'm not working for operator, I'm working for the Juniper. Can you emphasize a little bit about the impact of the VM motion, moving VMs on the signaling in option C?
Okay. So in the option C, okay, first in the VM is a move that's already supported by within the data center technology, right? That's now you're saying that if that VM will exchange, talk to the external, then
the VM moves from one host to another, right?
Yeah.
Ultimately, it means that the tunnel has to be,
Point.
other tunnel has to be used, right?
Yes.
So every VM move, which is a center of the efficiency of the virtual data center, when you move the load, when you have the resources, every VM move is immediately exposed to every single one PE, all right?
Right.
Because the BGP next hops change, and this goes across the one network to every single PE, right?
True.
That's a consequence of the option C.
That is true, yeah, because yeah. So whenever that's changed, that's also required, that's the BGP to exchange this, the banding information to the remote, the PE. So that's this implementation reality, yes.
And we just for the record, we are option B or A. We somehow hidden this churn behind the gateway.
Yeah, thank you. Thank you for pointing out that. Yeah. Any other questions? Okay, thank you.
I promised I'd talk really, really fast. But I do think it's important to give an update on where we're at with OpenIX for people in the room that are interested, and it's pretty good. So we now have 5 IXPs certified, including 1 international with AM6 in Amsterdam. We still have 1 pending with Flix, and we have 3 others that are announced. On the data center side, we're now up to 24 data centers. We have some notable new additions since our last update with DataGrid and Sabi. We have a number that are pending and coming along, including our first international data center with Jaguar Networks in Marseille. Very excited about that. We've got a number of data center evaluation tools. We're going to be announcing those more in the next few weeks, and they'll be available on the website. Marty and Hannigan and David Diaz and many others put a lot of work into a questionnaire that really goes into some of what you might call the soft factors, but are very important in your decision matrix. So, you know, what the communication capabilities, service capabilities, turn up, access, energy, human factors all around the data center to help you evaluate it beyond the pure structure of the certifications that we do. We're also, in the next few weeks, going to be implementing a more specific transparency and complaint resolution process. I won't read this to people, but basically, if you see anything that's not right with any of the data centers that doesn't meet the requirements of OIX-1 or OIX-2, we encourage you to either named or anonymously report that, and we do now have a formal process to take that up with the provider. We've built it in a way so that it won't be hurtful. If it's a false complaint, we'll pull that out quickly. But we've also built it to be very thorough and to have a specific timeline behind it for resolution. And we think that's important in the face of the fact that these are really self-reporting standards. So if there's a problem with that self-reporting, or if something changes over time, we need to really rely on the community to help police that for everybody else in the community. And just in conclusion, and I'm almost going to make 5 o'clock, we're also looking at standards refresh, standards expansion. We're having a lot of discussions about, what should we wind into the existing standards to strengthen them, or should we have other standards to deal with specific requirements. There's been circulated lately comments on both the single-corded lineup and reduced reliability, really the end discussion we had here today, as well as virtual pairing and variants thereof. And there's pretty heated debate and strong opinions both ways. Other things that are starting to come on our radar screen and we're starting to take a look at are really how we look at remote operated facilities, lights out facilities, basically facilities that have no personnel on site. We do see there's a role for those, both domestically but internationally as well, and so we're going to be thinking about that. As I said, we want to both strengthen the core standards and continue to identify issues and concepts and cases that impact a significant number of the constituents. And we're pretty open whether that significant number is 10% or 25%. We haven't drawn a line yet, but if they're real issues, we want to put them on the table to consider. So with that, it is 5 o'clock. We're wrapped up. I'm glad to take a question if anybody has one, but thank you very much for coming to the data center track. Appreciate it.